Okay, welcome everybody for the session Coverage-Driven Verification. My name is Stefan Bauer. I'm a field application engineer at Mentor, a Siemens business, and today I give you an introduction to a smart metric-based verification approach. In this session, we will answer the following questions. What is coverage and why should we collect it? Then we will talk about what is code coverage and functional coverage. And in the end, I want to show you how to use functional coverage with UVVM. So let's get started and let us answer the question, what is coverage? During a project, you or at least one of your colleagues need to answer the following questions. Were all the design features and requirements verified? Were some lines of code or structures in the design model never exercised? When we tested feature X, did we ever test feature Y at the exact same time? Has our verification progress stalled for some unexpected reason? Are there tests that we could eliminate to speed up our regression suite and still achieve our coverage goals? I assume that all of you needed to answer at least one of these questions. But how can coverage help you, and what is it exactly? Simply speaking, coverage is the metric we use during simulation to help us answer the questions from the previous slide. Or let's rephrase that a little bit. Coverage is a simulation metric we use to measure verification, progress, and completeness. Coverage metrics tell us what portion of the design has been activated during simulation. That is the controllability quality of a test bench. Or more importantly, coverage metrics identify portions of the design that were never activated during simulation, which allows us to adjust our input stimulus to improve verification. When we have a look into the document Advanced Verification Methods for Safety-Critical Airborne Electronic Hardware from the FAA, we find different types of coverage and the steps which we need to do for coverage analysis. I strongly believe that these steps are mandatory for all projects and not just for DO-254 ones. But I will not go through all of these steps, I just want to mention some keywords. First, you should look for unreachable code, because it might be that it was not your intention that this code is unreachable. The goal for code coverage is 100% here, and you need to document if this is not possible. The goal for assertion and functional coverage is 95%. Of course, you should define your own coverage goals. But remember the words from my colleague Harry Foster, who asked you if you can live with a roof on your house which is not 100% waterproof. Today, I want to go through exactly these three coverage types you can find in this document. But before we dive deeper into the different types of coverage, I would like to share with you slides of the Wilson Research Group study. This slide shows you how many FPGA design projects use code coverage, functional coverage, assertions, and constraint random. You can see that more and more projects are adopting such advanced verification techniques. Code and functional coverage, which you see here, are used by more than 70% of the FPGA projects today. But what do these numbers show us? I would assume that the quality of FPGA projects is increasing year over year. Or in other words, I would assume that less bugs are found after code freeze. Luckily, the Wilson Research Group asked the FPGA participants how many non-trivial bugs escaped into production. The results shown here are somewhat disturbing. In 2018, only 16%, what you see here, of all FPGA projects were able to achieve no bug escapes into production. And for some market segments, the cost of field repair can be significant. For example, in the mil-aero market, once a cover has been removed on a system to upgrade the FPGA, the entire system needs to be revalidated. You can see that even if many FPGA projects already adopted advanced verification techniques like code and functional coverage, the quality of code leaves a lot to be desired. The reason for this can be that the adoption of such techniques are not efficient enough. For example, a project has adopted functional coverage, yet the fidelity of their functional coverage model might be poor due to their inexperience. To avoid that you become one of the 84% with non-trivial bug escape, I will go now into the details of code and functional coverage, simply to improve a little bit your experience with these techniques. So let's talk quickly about code coverage and the different types of it. Code coverage is an automatic technique that identifies code that hasn't been tested. It does not require a change in your current design or test bench or simulation approach. You simply need to add a command line switch to your compilation. You see here for vcom you need to add +cover, and you can define the different types of code coverage. By the way, you can do the same if you have Verilog. With vlog you can also add the +cover switch. For simulation, when you start simulation with vsim, you enable to collect code coverage with the -coverage switch. So let's quickly go through the different types of code coverage. The easiest one is statement coverage. Statement coverage counts the execution of each statement in a line individually, even if there are multiple statements in a line. You see examples here. So, a statement ends always with a semicolon. You see here that's one statement, and in this line here you have two statements. Branch coverage counts the execution of each conditional if-then-else and case statement and indicates when a true or false condition has not executed. In our example, it's this one here, the if count is smaller than 4. FSM coverage counts the states, transitions, and paths within a FSM. You see, we can also visualize the FSM and makes it easier to debug. Condition coverage analyzes the decision made in if and ternary statements and can be considered as an extension to branch coverage. Expression coverage, it's quite similar to condition coverage. It analyzes the expressions on the right-hand side of assignment statements, and as I said, it's similar to condition coverage. Last but not least, toggle coverage. Toggle coverage counts each time a logic node transitions from one state to another. So let's quickly go back to our vcom +cover switch. Now you see what the letters after the cover means. So you see that's branch, condition, FSM, expression, statement, and toggle. So whatever type of code coverage you want to collect, you can simply enable this specific type by adding the letter to the +cover switch. And if you don't want to collect it, you simply remove this letter. So it's that simple. The result of code coverage can be analyzed in different views in ModelSim Requester. The first one is the code coverage analysis window, where you can switch between the different code coverage types. You see in my example that I did not cover any of the statements. That's why they are marked with a red X here. It's simply because I haven't executed any test case. In the instance view, you see all the information for each code coverage type by instance. For example here, the statement one. And also you can see the total coverage for each statement here. In the source code window, you see the green marks here. These indicates that this specific code coverage type was covered. If there would be a red X similar to this one here, this will indicate that it's not covered, so you need to debug and you need to figure out why it was not covered. Of course, you can also create a text and an HTML coverage report, and you can also merge the code coverage results of different test case runs to get a full picture of all your tests. We will talk about these topics more in detail in one of our follow-up sessions. So, that was all about code coverage. Now let's talk a little bit about functional coverage. So why should I bother about functional coverage if I collect already code coverage? Good code coverage does not automatically indicate good verification. Functional coverage measures what you have applied and what has happened, and it guides you to create better stimuli. On the one side, it's not an automatic technique as code coverage is, so the user really must write functional coverage code. And that's what I want to show you in my next few slides, how to do that. When we talk about functional coverage, there are three types of functional coverage. The first and the obvious one is direct tests. That means, have I run my directed test cases, for example, a reference vector set? That's already a kind of a functional coverage item, because you test a specific functionality of your DUT. The second one is control-oriented coverage. With control-oriented coverage, you can answer questions, have my assertions evaluated? Or have I covered all the interesting order of events? The last one is data-oriented coverage, where I answer questions like, have I generated all types of transactions? Have I read and written to all addresses in the address map? What type of data and settings have we tested? And you can also cover sequential combinations. In my next slides, I want to go through the last two coverage types. So, let's have a look at control-oriented coverage. As I said, control-oriented coverage is based on assertions, which means on properties. You can collect this type of functional coverage with the PSL language or with SVA language. If a property is asserted and never fails, but can be shown to complete, means it passes all the time, functional coverage can be assumed. If a sequence completes, then the functional behavior encoded in that sequence has been observed. That's a covered directive. So let's have a look at the simple property or sequence. I have my request signal here and the acknowledged signal there. So my sequence says, as soon as the request signal goes high, the acknowledged signal must come 1, 2, or 3 clock cycles later. And such a sequence I can easily cover and use as functional coverage. Now, I quickly want to show you the differences between the assert and the cover directive. I know that this example is SVA, but you can use PSL in exactly the same way, just there's some differences in the syntax, but from the usage point of view, it's exactly the same. So, let's have a look at this property here. We check at each positive edge of the clock. We check if the request signal goes high. If the request signal goes high, I'm waiting another clock cycle and check if the acknowledged signal follows. That means it's exactly the thing what I've shown you in my previous slide. Request signal goes high, within 3 clock cycles the acknowledged signal must follow. So when you run your simulation and when this property will fail, due to the assert here, you will get an error during simulation. But if this property never fails during simulation, you can assume that it's always passing, and so functional coverage can be assumed. We can also use such a sequence to cover corner cases. So let's slightly modify the property. Let's use sequence here, and we're adding a parameter n. N is the delay between the request signal and the acknowledge signal. So you see it here, I'm covering now my property. Property is sequence with 1 clock cycle delay. The same here, I cover if the sequence with 3 clock cycles delay. So let's run a simulation. When you run a simulation and the acknowledge signal follows the request signal 1 clock cycle later, this specific cover item will be incremented. The same if the acknowledge signal follows the request signal 3 clock cycles later. The other one, this one will be incremented. But what if the acknowledge signal follows the request signal 4 clock cycles later? Nothing will happen here with the cover. The cover simply will cover if the sequence occurs. If it does not occur, it will not do anything. This property here, because of the assert, this will give you an error if this sequence is violated. And that's the differences. So in ModelSim and Questa, we provide you a cover directive window where you can view and analyze the status of your current cover directives. That means we will add these 2 items you will see in the cover directives item, and in the end you will see if you have fully covered it or not. Next, let's have a deeper look into the data-oriented coverage. With data-oriented coverage, you need to answer the following questions. Which values are important? Are there dependencies between data variables? Are there boundary conditions that should be checked? Are there illegal conditions? Are there conditions that are not important? When should I sample the coverage? Are there times when the sampled data is not valid? But what exactly is data-oriented coverage? To answer that, let's have a quick look into a smaller example. Data-oriented coverage records the values of variables at particular points during the simulation, and it usually captured by the test bench. Let's see the principle here. For example, we have a signal A with the legal range 1, 2, 3, and 4, and a signal B with the legal range 1, 2, and 3. The blue boxes here are representing the single cover bins. For example, this box here represents the cover bin for the value 4. As soon as the coverage is sampled, the current values of A and B are compared with the cover bins, and if there is a match, the related bin is incremented by 1. With that, you can find out how many times did A won. In our example, it was 3 times, what you see here. Besides the simple coverage, you can also see transition coverage. This tells you how many times did A equal 2 after A was equal 1. You can also collect cross coverage. That shows you each possible combination of signal A and B. If you only cover A and B without crossing these two, you might say that A and B are fully covered, and you do not have any coverage hole. But if you collect cross coverage, you will find out that you did not cover the combination A is equal 1 and B is equal 2. With my next few slides, I will go through some examples how you can write functional coverage. I will show you a syntax which can be used in VHDL, in Verilog, or in System Verilog. It's up to you. So let's get started with the example. In the first example, you see a cover group. A cover group in general is, you can see it as a container which contains cover point and cross items. This cover group here is simply sampled at the positive edge of the clock. Just as a side note, I would not recommend to use the clock as a sample event. It simply will generate such a huge amount of data, which you definitely do not need. So again, you really need to think on which event you want to sample a cover group. The cover group contains, in my example here, a cover point. And I want to cover the signal active. Active, it's a standard logic, so we can have the values 0 and 1. And that is why I have added two bins, one for idle and one for active. And I also name them to idle and active. So now, if the active signal is 0, the idle bin will be updated. If the active signal is 1, the active bin will be updated. If you debug this later on in the GUI, we have a cover groups window, and you can see again the naming bins here. So the first bin idle and the second bin active. Makes it much easier to debug. You also can see the status of my coverage. So I have 0% in my example, simply because I have not covered anything, which means for me I have not run any test bench so far. Now let's have a look at my second example. As I mentioned on my previous slide, to use the clock as a sampling event, it's not the best choice because you generate a huge amount of data. So here in this slide I want to show you how you can use a sequence as a sampling event. This sequence here indicates a bus access. That means the CS signal goes high and one clock cycle later the CS signal goes down again. And I'm simply using this sequence as a sampling event for my cover group. In my cover group, I have again a cover point for my operation. My operation in this case can be write and a read access. Depends on the signal value of write enable. Again, I will increment the write bin or the read bin. You also see here that I have a cover point for my address. Per default, as I did not add any bin here, you will get 64 bins for this specific cover point. And then, of course, I'm interested in if I have read and if I have written to all parts of my address map. And that's what I do here with my cross item. So I simply cross the cover point operation with my cover point address. The big advantage of crossing cover points, as you see here, is that if I need to update a cover point, let's assume we add some cover bins to this address cover point to define specific ranges which I want to see. It is automatically applied to this cross item here. So you do not need to take care on updating this cross item as well. It will automatically be applied to that. So less error prone. And think about if you have multiple cross items for the same cover point. You only need to update one cover point and it's automatically applied to all the cross items. Now let's have a look at the cover groups window and how the automatically generated bin and the cross item are displayed. Here in my first window you see my automatically generated cover point for the address, and you will find 64 bins for these addresses. They are using the bin name auto and the specific range for the address. If you look down to this window here, you will see the cross item between the operation and the address. This cross will contain 128 bins because it's automatically crossing the operation and the address. The result name for each bin is write auto 0 to 3, write auto 4 to 7, and so on and so on. Now, as I said before, big advantage on crossing cover points is, what if you update address range? It will automatically apply inside the cross item here again, and you will see different ranges here. So again, quite easy to debug. Now let's have a look at my third example. Many times you're interested in sequential operations. Let's take a small example. We have an enum with the name color, and this enum contains the elements red, green, blue, white, gray, and black. And I'm interested in the sequential operations, which means red followed by green, or green followed by blue, and so on and so on. For that, I can create another cover point for my color. I'm adding a bin called C_sequence, and here you see that's an open array. And the bin should contain the following sequence: red, green, blue, white, gray, black, followed by red, green, blue, white, gray, black. And if you look at the cover groups window later on, you see my cover point color sequence, and it's automatically generated. The bins here means C sequence for black followed by black, black followed by gray, black followed by white, and so on and so on and so on. So it's quite easy to write one line of sequence, and it's automatically adding a lots of cover bins for this specific sequence. As I said earlier in my presentation, this syntax here can be used within Verilog and System Verilog, but it can also be used within VHDL. And that's what I want to show you in my example, because I have a UVVM environment up and running, and I want to show you how you can use this syntax within a UVVM environment. I'm using the Bitwist UART example, which you can find in the UVVM download. The test harness looks like that. You have the DOT I_UART, and you have two VVCs, one for the SBI and another one for the UART. The UART VVC can transmit data to the DOT, and it can receive data from the DOT. The reason why I took the UVVM UART example is that it also includes a monitor, and UVVM itself is using transactions. This transaction for the UART contains the operation, which means for the UART a transmit or receive. It has the data. It has some meter information. It has the transaction status, which means passing, failing, in progress, and it has error info, which means parity or stop bit errors. To collect functional coverage with this UVVM environment, I added a component coverage collector to my monitor. You see it here. This coverage collector gets the information from the transaction, and it will collect functional coverage. But how does the functional coverage look like, or how can you write it for this transaction? That's something I want to show you on my next slide. Functional coverage, as I told you in my previous example, is based on cover groups. A cover group, again, is simply speaking a container of cover points and cross items. There is also a predefined function called sample, and when you call this function, it will provide you the T-based transaction item, which is the record here. So again, you have access to all the signals from the record. The next step is to think about which item of the transaction you want to cover. In my example, I'm only interested in the operation, the data, and the error info. So let's write a cover point for the operation. I named the cover point operation CP, and I want to cover from my record item the operation signal. I add bins for my operation, and it can have the value receive and transmit. Then I added another cover point for the data. You see that I added 3 bins for the lowest values and 3 bins for the highest values. And I also want to create 20 bins for this specific range of data. I'm also adding cover points for the stop bit error and for the parity bit error. And last but not least, I also created a cross item. You see that I cross the data and the operation cover point. The result will show that I've covered all data bins for transmit and for receive. Then you run a simulation or even a full regression and you get your coverage result. You can analyze it with the cover groups window. You see that with this functional coverage approach, you get instance-specific coverage. You see it here. This means that I get functional coverage information for the transmit coverage collector, and if I would add another instance of the same coverage collector component, which I, by the way, did not do in my example here, but I would get another instance-specific coverage result similar to this one. And I would also get the total coverage, which you see here on top of it, for all the instances together. Now let's quickly match the cover group code here to the coverage results here. The first one is the operation cover point. And again, you see we reusing the enum from the transaction VHDL transaction package, and the bin operation you see transmit and receive again. So it's readable. Data cover point, it's the next one. You see that I have my lowest values, data 0, 1, and 2, my highest values, these three here, and I have my range where I created 20 bins. They are named like this, 0 to 19. Then I have cover points for parity error and also for stop bit error. And here you see my cross, where I cross data and operation. And you see how we name that. That's data 255 crossed with operation receive and 255 crossed with operation transmit. So again, if I change something here in my data from my bins, it's automatically applied here in my cross item. And think about if I have multiple instances of the same coverage collector which I want to merge together. You only need to update one source to get it applied to all instances and to all cross items. Similar to the code coverage results, you can create a report for all coverage types together. Here I want to show you the text report for the cover group, which gives you a good overview of the final coverage result. But you can also create an HTML report, which gives you a nice view of the coverage results. As I said in the code coverage section, I will not go into the details of reporting. We will have another session on this topic. Let's summarize this session. Functional coverage and code coverage have pros and cons. Functional coverage measures completeness of the design functionality. It is reusable because you can create multiple instances of the same coverage collector, or you can use it from a block level test bench up to a top level test bench to get a full picture of your functionality of the full FPGA. It is encapsulated and it is tied to specification, which means if you're working in a safety critical application and you need to fulfill certain requirements and you need to do requirements tracing, you can easily link them to functional coverage items, the requirements, and you can show that you have covered all the functionality what you need to cover. Cons of functional coverage: it's error prone because humans need to write this code, and as soon as somebody manually writes that, it's only as good as the engineer which is in front of the laptop. It requires a test bench and it's unable to identify unexercised code. Let's go to code coverage. The pros on code coverage are that it's automatically collected by the tool, so the engineer does not have to do anything except enable a switch for compilation and simulation. And code coverage identifies unexercised code, which has not been tested then. Cons are it's unable to measure design functionality. So you can be sure that you have exercised a certain piece of code, but you don't know if it's functionally correct. And with code coverage, it's unable to identify if all conditions have been tested or not. The good thing is, functional coverage and code coverage do not compete against each other. It's the opposite, which you see here. You really get the best quality of your code if you collect both of them together. Before we go to the Q&A session, I want to share with you some links where you can go to learn more about this topic and others. Verification Academy is definitely the best place to go to learn more about methodologies. With Verification Academy, we try to focus on methodologies and not so much on our tools itself. If you want to learn more about our tools, you go to mentor.com/products/functional verification or /FPGA. That was all from my side. Thank you so much for your time today. And yeah, now let's open the line for Q&A. Thank you.